Hello, AP Physics. Today we are going to be talking about forces and circular motion and how those two things interact. And there's going to be several different examples that I'm going to work through here in the general that then you can work out in the specific numbers later on. So the first one that we're going to be dealing with is a car driving around a corner. So we know that this car, if it's going to be going around a corner, it's going to need some acceleration so that it can turn. The velocity is going to be changing direction, so it can't continue to turn unless there's some sort of force pulling it into that circle. So let's draw a force diagram that represents our car here. Since our car is on the road, what we're going to do is we're also going to draw another picture that is looking from behind the car. Okay, so here's my box car, right? There's my person's head. Here's the window. Cool. And then my tires. And we're going to draw the forces that are related to this. So we have the force of gravity pulling it down. And our car is not accelerating upwards or is sliding down an incline. So the force normal is going to be equal. I think I drew that a little bit bigger, but we'll just say that they are the same size here. Okay. Now, if my car is going to turn to the left, I need some force that is going to push it in that direction. And the car's wheels are in contact with the road, and they are made in such a way that there's going to be a significant amount of static friction. Now, remember, I mentioned that friction opposes slipping. The cool thing about wheels and why people talk about wheels being such an advance in technology is that you don't have to cause them to slip across the ground, to slide them across, right? They roll. If you looked at a wheel, you'll notice that one point on the wheel comes in contact with the ground and then lifts off. So static friction is never broken. So when you're dealing with a car that isn't slipping, that means that you have a force of static friction on your car. So I'm going to call it force of S for static friction. That's what our book uses. And so this is what we want to see. If we are going to be turning, we actually need some friction here. Now, let's think about this for a moment. Let's say it was ice, right? Right? Or even some compacted snow, right? When the Phoenicians come up here, they think that the force of static friction is still present. But unfortunately, what occurs is this force of static friction gets much, much smaller. Right? And when it gets smaller, if my force of static friction exceeds my force for circular motion, right? Force of circular motion, we write down as mass equals velocity squared over radius, right? If the force of circular motion is greater than my force of static friction, this is going to cause it to slide. Okay. So if you want to go around in a circle, or if you want to turn, you're going to have to go slower on that ice. This is why when we're downtown, you are not going to take that turn as fast as you would today in early fall, or actually it's still summer, right? So, right, late summer, as you would in the middle of winter, because your force of static friction is going to be much, much less. And so you're going to break it. And that is going to cause you to then have a force of kinetic friction, which is less. So in the textbook, what they do is they solve for the maximum turning force that you can have. And actually, I can get rid of my car here because I don't need it anymore. They solve for that maximum turning force, and that is what we're going to be doing here, so we can see how this works out. The first thing that they do in the problem is they identify that the force maximum is going to be equal to, right, our mu in the static friction of that normal force, right, is equal to the force of circular motion, right? Notice this should look very similar to the binary stars if you remember back to that that unit we did in 9th grade, right? So we have, in that one, we had the force of gravity is equal to the force of circular motion, okay? So we can then look and we can notice that the normal force is also equal to the force of gravity, which we identify as mg. So now we can substitute a couple of things in. So we can take our force normal and we can substitute it in for mg. So mu of static friction times the mass times gravity is equal to mass times velocity squared over the radius. Mass on both sides, we can cancel out, is no longer needed. So now we can figure out how fast we can turn around this corner, right? So we want to know the maximum velocity. So we can solve for that. So it's going to be mu of static friction multiplied by gravity and multiplied by our radius, right? We had radius on the other side. So this gets us velocity squared. And we don't want that square anymore. So we're going to do the square root of our answer. And that is going to get us our maximum velocity. The second example that we're going to be looking at is what's called a banked turn. Now, a banked turn is very similar to a regular turn on a level ground, but instead it has an angle to it that is turned towards the center of your turn. So what does this look like? Let me show you. So in this situation, it is going to look very similar to a box on an angled incline. But here are going to be a couple of different things. So the first part is that we want to be designing this roadway kind of like in the book where friction is not involved. We can include it. It's going to make it more complicated. So we're going to deal with a simpler situation here. So the first force that we always know we have, as long as we are on Earth, is that there is a force of gravity pulling down, right? Now, the car is not going to be sliding down, and we are eliminating the need for a centripetal friction force like we had on the non-banked turn, right? A turn maybe in the downtown of Flagstaff. On here, we're not going to have that friction, so we're not going to consider it. So this means that my force normal is going to have an even component to gravity in this vertical direction. And if I want to draw my force normal, it's actually going to be bigger than my y component here, my force of gravity. Notice that from those two situations, right, we normally have a force normal on the side of a hill that is less than the force of gravity. And that's because we don't have a centripetal acceleration, right? There's only the force of gravity pulling it down, and the force normal is resisting that a little bit. It's that passive force. But here, we are going to have a centripetal acceleration caused by the car's motion, and then we're going to have a y component of the force normal because of the force of gravity. So this portion and this portion are the same. So F and Y, and F and X. Now, something that should be shown here is the difference between this car and a box on an incline. So here I'll draw my triangle over here. Here's my box, right? And on this box, we have our force of gravity, and we have a force normal coming off of here. And let's say we have our force of static friction, right? It's not moving. So in the example here, we changed our axes so that parallel with the incline was the x-axis, and perpendicular to the incline was the y-axis. Now, this was helpful because we cared about the box sliding and not sliding down the hill here. And so it was simpler for us to do it this way. But in our car example, we need to make sure that we keep the horizontal portion horizontal with the Earth, because our circle is moving in that direction, right? That is going to be the direction of circular acceleration and circular force. So we need to keep it there. If we change our axes, we won't be able to deal with it like we do in the previous unbanked example. So now that we understand why we have done what we've done with the directions of our forces, we can start solving the problem. So just like before, we know that the force normal in that x direction is going to be equal that force of circular motion. So we can write that down below, is that the total force normal, and this is, right, I'm going to put my angle here. That's where the angle goes. The force normal sine of theta is equal to the mass times velocity squared over radius. We know those two things have to be equal if we don't need any friction. Okay. The next portion is going to be the forces added up in the vertical direction, the y. And we know that adding them up, they're going to equal 0, right? It's not sliding down or up the hill. So that means that the force normal in the cosine direction minus mass times gravity is going to equal a force of 0. They directly cancel each other out. Or we can set them equal to each other. Fn cosine of theta equals mg. Okay. So now that we have these two things, we don't know actually what the force normal is totally equal to, but we can if we use our trigonometry and a system of equations here. So we can divide one over the other. We will do sine over cosine. So this is going to look like Fn sine of theta over Fn cosine of theta, right? Fn's cancel out, and we have m v squared over r divided by mg. So we can simplify this out. Sine over cosine is going to give us tangent of theta, and our masses cancel on this side. So we are left with velocity squared over radius times gravity. So that's our answer. Now, I want you to notice just in general for problem solving how I work things out, and the book as well works things out in terms of the symbols. So we call this a symbolic answer, and then we can plug in our numbers and we can get our numerical answer. So there are two kinds as we solve them, and I would recommend that you solve it out symbolically first as much as you can, and then plug in your numbers. That will help things to be simplified, and your calculator won't be doing as much rounding, or you won't be doing as much rounding as you solve. The next problem that we're going to be solving is one involving an amusement park ride, and usually this is at like traveling amusement parks where you have a spinning cylinder, so you can stand up on the floor, but then there is a cylinder on the outside, and I'm going to draw it here, right? So here's our cylinder. There's a central thing that's spinning around, right? So it's spinning. And you can stand up here if you want, but at some point, the ride is going to be spinning so quickly that you can actually, wait, can I pick you up? No, I pick up the whole thing. Shoot. That you can actually stand up on the edge. Something like this. Now, how can this occur, right? It is occurring because of the circular motion, and the circular motion is going to be causing a centripetal acceleration, a centripetal force, and we're going to be looking at that here. So let's draw a top-down view here. And here's our dude standing in the center, or on the edge of our circle, right? So they're actually horizontal in this case, right? This is a top-down view. So we know, since there is circular motion, that there's going to be some sort of centripetal force pushing him in, right? And if he's over here, right, then there's going to be some centripetal force pushing him in. So if you think back to our previous video on friction, this situation is going to look pretty similar, right? If I have my book up against a wall, right, I have a force normal that is pushing out, and friction is keeping me up compared to the force of gravity, right? Force of friction and the force normal, okay? So we have these forces, and these two are in equilibrium. So what is happening with our guy on the edge of the ride here? So let's scoot that drawing over. And let's draw a new drawing with our dude standing up on the edge of our amusement park ride. So we know that there is a force pushing him this way, right? We're just going to call that force centripetal. Then we're going to have a force of gravity pulling him down, right? Gravity's still acting on him. So these two forces right now show us that he should be moving down and to the left, right? So we can draw that addition of the forces here. That would be the net force. So he should be moving in, but he should also be falling. But when people are on this ride, they don't actually fall. They stay there. So there must be another force that is keeping him upright. Now we can start figuring some things out. One is that this force centripetal is actually perpendicular to the surface of our wall. And so that makes this force centripetal actually a force normal, okay? Now, because we have a force normal, we are going to have some friction, and if our person isn't sliding, then the force of friction is going to resist that sliding. So they're going to tend to slide downwards. So that means that the force of static friction is going to be pushing upwards, and it will be equal and opposite to the force of gravity. Now, this is not a Newton's third law. Remember that, right? Newton's third law is two forces equal and opposite on either object, one force for each, okay? So this is what is going on in this problem, and we can solve for our minimum force normal to get a force of static friction equal to the force of gravity. So let's try that out. First off, let's move our drawing over to the left here so we have some room. And in this case, we know that the force normal, again, is going to be equal to that mass times the velocity squared divided by radius. And we also know that the force of static friction, which is going to be mu s times that force normal, is equal to mass times gravity. So now we have a system of equations. We can solve for what our minimum velocity going in a circle is going to be so that we have this, this standing on the edge. So we can already do some substitution. We know that the force normal is equal to that mass velocity squared divided by radius. So let's substitute that in. We get mu s m v squared over radius is equal to mass times gravity, right? Notice we have mass on either side. See how often this goes away? And we want to solve for that velocity. So we're going to have velocity squared is equal to radius times gravity divided by mu s. And then we'll do the square root. So velocity is equal to square root of radius times gravity over the mu of static friction.
So let's think back to freshman year. We did a unit on circular motion, and we were looking at binary stars in particular. What we found was that if we want these stars to have a good orbit, we want their force of gravity to equal their force of circular motion. Okay, often we just said that the g was equal to the velocity squared divided by radius, right? And that makes sense since the mass and the mass cancel out here. So let's look at our example again. We had a binary star that was smaller and another one that was bigger. And then we had some distance between their centers, right? This was the diameter. And usually the center of mass, and always the center of mass is their center of rotation. Okay. So we have one radius and another radius. The bigger star obviously had more mass and the smaller star had less. So when we are looking at these forces of gravity, since forces of gravity are Newton's third law pairs, right? We can draw the same force on either one. And they would be equal and opposite in size. Now, one of the issues was that the velocity of the small star was much bigger. So we'll draw the velocity coming off here to be pretty big. And the velocity of the big star was much smaller, right? Well, this seems to all balance out. Remember, we have our velocity squared over radius. So let's look at the small star first, right? We have some force of gravity here, and this is equal to its small mass multiplied by its large velocity squared and its large, or divided by its large radius. Then for the big star, right, we had a large mass and a smaller velocity and a smaller radius. So these two things cause them to balance out. They end up having the same force of gravity, which means that they will also have the same acceleration and force of circular motion. Now, if I wanted to find what the particular velocity would need to be for a particular acceleration of gravity, well, I could use this equation at the top and solve for velocity. So it would be velocity equals the square root of g and r. Notice that this is the exact same equation for the roller coaster problem we solved in class. So to sum up, we are going to be looking at a couple of problem solving tips for circular motion problems. The first thing that I want you to know is that anytime that we're summing forces, especially in the direction of, and actually only in the direction of the center of our circle that we're moving in, that this net force is always going to be equal to our centripetal force of mass times velocity squared divided by radius. Okay. Now, the other ones, they are always going to add to zero. So whatever that sum of forces is, those are going to add to zero in the other direction. So you'll see this kind of form every single time. And if you look through the problems pretty quickly, you'll notice this too. The reason why this is the case is because our object will always be accelerating in the direction of the center of our circle. And then we don't want it accelerating in the other portions because it is a object moving with a constant speed, but in that circular motion.